We will continue with the CMOS. About the operation, we already talked about the operation, and now we will look at the fan out. And as we discussed, the fan out is limited by the switching time. Since the current here is 0, IG is equal to 0. This IG is equal to 0. Therefore, the current is not limiting our device. The device will be limited, the operation speed. It will limit the fan out, actually. Of course, if you connect more than one, inverter here, or maybe NOR gates or whatever, it will be loading. The capacitances will be adding up and then will create a delay. So maybe I should do this. IG is equal to 0. IG is equal to 0. Okay, so the limit will come from the capacitance, and the capacitance is actually going to be this. One of them is going to be this one. C. We call it C gate capacitance, and then C gate of N, let's say, and then C gate of N is roughly equal to W times L times C oxide. This is the gate oxide per unit area. So relative permittivity of oxide times relative permittivity of free space divided by the oxide. So that's for the N transistor. And interestingly here, we have the P transistor. So there's going to be also this capacitance, C gate of P. And C gate of P is going to be roughly equal to WP times LP times, again, CO divided CO. But we have two of these capacitances. What is CL? CL, if there is only one gate, let's call this thing CL, or let's call this capacitance that we see here as CL. That CL value will be equal to C gate N plus C gate P. Okay, so why is it the case? Although one side is connected here, the other side is connected here. Because if you think about the AC analysis, if you want to find the delay here of, let's say, this kind of circuit, VDD, and let's say C gate of N, C gate of P, and let's say if we have a resistor here, okay? So what is the time constant here? R. The time constant will be, tau will be equal to R times C gate P plus C gate N. Okay, if there was any tau. So basically, for the AC analysis, this is ground, so they just add up. Okay, so we consider this as if you have this. Okay, C gate and C gate P. So CL will be therefore is equal to, let's call this whole thing as C equivalent. So CL, if there are more than one gate connected, CL will be equal to N times C equivalent. So this is fan out. So you know that fan out can be maximum fan out or can be just fan out. If there are two inputs connected at the output, then its fan out is going to be 2. So this is how we calculate here the CL. So here for this analysis, we assume nothing is connected here, just this one. So maybe I should say that this is C equivalent. Okay, so CL will be equal to C equivalent. So that's how we calculate the capacitance, and the capacitance determine the delay time, and then the maximum operating frequency. So the fan out will be determined by maximum operating frequency. Maximum fan out will be determined by the maximum operating frequency. Required. Because if the operating frequency required is large, then we want the switching to be fast. So then CL should be small. Okay, if F is large, then CL should be small, because it determines the delay time. So when we look at the switching for this device, when this is, let's say, t is equal to 0, when t 0 minus, V out, which is equal to VCL at 0 minus, is going to be equal to, at steady state, VCC, or VDD, sorry, VDD. So when, because V in at 0 minus is equal to 0 volt. Okay, so at steady state, this is it. So what about when we in at 0 plus, it becomes VDD, V out, which is equal to VCL 0 plus, it will be also VDD, because the capacitor doesn't want to change its voltage immediately. So therefore, at t is equal to 0 plus, this is what we have. input is VDD, 0 plus, and the voltage here is going to be initially 5 volts, but then it will be discharged. How is it going to be discharged? Through here. So the discharging current is going to be initially IDS SAT. Okay, so we can use here the equation. So IDS current, IDS of N, VDS of N is going to be something like this. Here, this will be the current or equation. So this will be when it's VDD, this is V gate to source of N is equal to 5-volt graph. So this is the graph where V drain to source of N is equal to V gate to source of N minus V threshold of N. So V gate to source of N is equal to 5 volt. Why? Because this is 5 volt, V gate to source of N. So then we can determine this point. I wish I had drawn this in a larger area. Maybe I should do that again here. So is this again one more time. Just to be more proper. So this is V drain to source of N. This is I drain to source of N. And this is VDD line. And then this line is here is VDD minus VTN line. Why? Because this is V drain to source is equal to V gate to source minus VT graph. So when this one is V gate to source of N is equal to 5 volt line, therefore this one is gate to source is 5 volt. So this one is 5 volt, this one is 1 volt. Therefore this one is 4 volts here. Okay. So the current is going to be initially IDS SAT, but then the discharging current will be changing. So this is discharging current will start from here, but then it will be decreasing discharging current. Okay. The discharging current will be nonlinear and decreasing. So, so we can here notice that the output is going to be starting from here. It will be first like this, but then it will be decreasing. But when it decreases, first it will linearly decrease. Why? Because the current here in this region, it's flat and maximum. But then after that, this will be decreasing like this. Okay. Initially, linear discharge with IDS sat current. Okay. So we can calculate, I mean, we know the trajectory here. We know all the current equations here. So we can find 10% points easily. 10% point is this point. This is the 10% point. Why? Because 10% point is V out is equal to 4.5 volt. So if you want to do this officially with the equations, from here to here, from V out, you know, will be decreasing from there, let's say to 10% point, which is like here, 0.5 volt. Okay, so that's going to be, maybe I should have said 90% point. So from 90% to 80%, Mn will be in SAT. So there will be linear discharging. Okay, and then we can find that timing, and it's going to be very easy to find that value. Why? Let's call that time is T fold 1. T fold 1 is going to be equal to 4.5 minus 4 volts, so that's delta V times CL divided by the current IDS, which is beta n divided by 2, 5 minus 1 square. So that's how we find, let's say, the timing that comes from here to here. So this voltage decrease is going to be happening in TF1 time. So that's not the voltage that we are talking about. And after that, from 4 volts to 0.5 volts, Mn will be in linear. So the current equation will be nonlinear. So discharging current I ds of n will be equal to, what is that? What is beta? So maybe I should have said kn here, because that's what you know, kn. And then we gate the source, which is 5 volt, minus VTN, which is 1 volt, times VDS minus VDS squared divided by 2. So IDS of N will be equal to Kn times 4 times V out minus V out squared divided by 2. So, so it's not that easy to determine. So we do some approximations here, as we discussed earlier. So approximations, like, if this was linear discharge, so T fall, T, let's say, F1. So this is maybe TF2. Okay. So what we do is either we find that value accurately, and there are ways to do that. I mean, if you do this maybe the way that we do in VLSI design course, normally, I mean, that's this time is going to be maybe T-fold 2. But these are different than these capital ones. So maybe I should erase this. Oops. Maybe I should do this small so that I can erase locally. Okay. So this is one approximation. Assuming IDS remains SAT all the time. Okay, so sometimes we just take it and then multiply it by 2. So roughly finds that value, a little bit with assumption. So but if you look at this value, maybe I mean, do this analysis. I don't have a space left here. I wish I had one extra page, but typically maybe I'm going to write it here with the black thing. T fall 90% to 10% or thing is going to be approximately equal to 3.2. This is coming from the equations, times CL divided by Kn times VDD. Okay, so this is what it will come to if you do all this maybe nonlinear equation. Okay. Okay, so you are not supposed to know this. I'm teaching this in VLSI design course. But typically in this course, we will ask you about this time is what you need to find, or you need to do some assumptions to roughly approximately find that value. So I guess so this is from VLSI course. From VLSI course, that's what is coming to. In this course, we don't teach that. So the similar thing happens when input switches high to low. When the input switches high to low, initially output is going to be low. Initially output is going to be low. And then the device will be charging at 0 plus, MN becomes off, and then MP becomes SAT initially. So the same story goes here. So this will be our device. So this is going to be VDD, and this will be ground, because at T is equal to 0 plus, 0 volt, at T is equal to 0 plus. And then here, the capacitor CL will be charged. Initially, Vout is equal to VCL 0 plus is going to be equal to VCL 0 minus, which is 0 volt. Okay, so the device will be charged through here. Okay, so the device CL will be charged through. And the same story will be also valid here for the current. Now this is I source to drain of P. This current is I source to drain of P. And that will be equal to, like, a voltage like this. So this will be, let's say, initially 5 volt. What is this? V source to gate of P. Sorry. V source to drain of P. So this voltage, V source to drain of P, is going to be equal to initially 5 volts VDD, and it will be remain it will be, of course, decrease when the CL starts charging. And initially, I source to drain of P, SAT current will be here. So this voltage is V source to gate of P is equal to 5 volt line. So this will be VDD minus VTP until that. This will be discharging. So the discharging current will be nonlinear, and we can look at this 90% to 10%, 10% for V source to drain of P. Of course, V out is going to be equal to VDD minus V source to drain of P. Therefore, V out will charge. So TR is the time where V out charges from 10% to 90% of the voltage swing, which is 5 minus 0 volts, which is equal to 5 volts. So again, we can calculate that rise time. And if you look at the real, what happens here, again, here, this is going to be initially increasing linearly until which voltage? Until 1 volt, which is VTP, linear initially. Okay, but then after that, it will be decreasing like this. Okay, and then you know, if we want to calculate that 10% till maybe 90%, it will be this much time. So this is really what we call as T rise time. And calculating that is not going to be that easy. But you know, if you look at this linear charging, it will be like this. So it's going to be about, T rise will be about 2 times T rise maybe ideal. What is T rise ideal? If I source to drain of P was remaining constant at its maximum value, which is I source the drain of P sat value. So you know, this is how we can find, but from the VLSI design course, we know that T rise will be equal to 3.2 CL divided by KP times VDD. Okay, so this is okay. So if Kn is equal to Kp, then rise time will be equal to fall time. Okay. Maximum operating frequency, Fmax, is going to be equal to 1/2 times maximum of T rise and T fall. So that's how we determine this Fmax. Why? Because we want to have equal switching, let's say, times. So if the duty cycle is T, and if this is 50%, This is T divided by 2 and T divided by 2. Okay, so this is called 50% duty cycle. If that's the case, then, you know, T here, we have T fall, you know, if this is Vn. T fall should be less than T divided by 2, and T rise should be less than T divided by 2. So we have to select the maximum of them to determine maximum operating frequency. So the largest one determines Fmax. And of course, if the duty cycle is allowed to be different than 50%, let's say, this is, one of them is small, the other one is large, whatever. And then if this is T fall, and if this one is T rise, then Fmax is going to be equal to 1 plus T fall plus T rise. But this is not practical. So therefore, we prefer this definition. Okay. Oh, we don't like this one. So this is the delay analysis. We do the thing here also. Again, like, the same idea is also used for the calculation here. Maybe I should write it similarly. T fall is typically estimated as 2 times T fall ideal, where T fall ideal is equal to 4 volt times CL divided by I ds of n sat current. So that's what we assume. That's the current is constant. So like here, okay, where here TR ideal, maybe I should have written here, TR ideal is equal to delta V, 90% to 10% to 90% voltage here, 4 volt times CL divided by I, source of drain of P, in SAT. Okay, so TR or rise time is calculated like this. I mean, here we are doing some assumptions anyway, especially in the course. So maybe we can, just write the advantages of this CMOS into this space. Okay. The advantages of the CMOS logic gates or technology. One, the output swing is rail to rail. I mean, it is from ground trail to EDD. Okay. So this is independent of the design. That means WR ratios. Okay, no matter what. Okay, it becomes like this. So the second thing is that high to low is sharp. Okay. The third thing is the static power dissipation is 0. Why? Because output, I DD is equal to 0 when output is low and output high cases. Either NMOS is off or PMOS is off. The design is simple. No need for WL ratio calculations. Minimum size transistors will work fine. Will be enough to have proper operation, and therefore, since the minimum size transistors are okay, we have maybe small chip area. Is required. Okay, so these are the good things. Maybe disadvantage. Maybe we can call this thing. implementation to implement PMOS transistors in the process. But that's not a critical thing. Just to add a few more things, we input low is going to be about 1.75 volts, and we input high will be equal to 3.25 volts if VTN is equal to VTP and if Kn is equal to Kp. How do we make Kn is equal to Kp? Kn is equal to Kp if WL ratio of P transistor is equal to mu N divided by mu P of WL of N transistor. So typically mu N divided by mu P is about 2.5. So that's kind of the summary. So we will be giving a break here. And then after we come back, we will be implementing maybe other type of gates. Like up to now, we have seen inverters. We will see NAND NOR gates. Do you have any questions?
No.
Is that okay? Okay, so we will continue to show how to implement other type of gates here. So this is how we do. So here is a little bit different than the other gates. So we need to implement the complement of each transistor here. So if you remember, we talked about this here for the previous cases, how to make a NAND gate. This was A, this was B, this was VDD, and this was V out. Okay, so this was our load. That was the case for previous circuits. But here we need to implement both NMOS and PMOS for each of the input signals. So if the input is low, we can maybe even make some cases for the PMOS and NMOS. We really don't need to, but just if you want. So this is MNA, MNB, MPA, MPB transistor. So we can write this MNB, MPA, MPB. Okay. Let's say now we don't need to say low high. We can just say 0, like, or we can just, yep, 0, 0. 0, 1, 1, 0, and 1, 1. So if you look at this case, if any one of them is 0, if any of inputs is 0, then no current through here. So IDS will be equal to 0. And if any of them is 0, then this will be pulling up. Okay. So if any input 0, then the output will be pulled up to VDD. Therefore, I mean, you can, if you want, we can fill that form, or we can just write output as you know, output is going to be VDD. For example, here, if A is, this is going to be off, this will be off, this will be linear, this will be linear, and therefore it's going to be the case. So if this is the case, this is again VDD. This is the case, again, this is going to be VDD. And now maybe you should say low voltage, 0 volts, 0 volts. Here is VDD, input voltage. Here is 0 volts. So logic-wise, it's 1. So this is 0 volt. This is VDD. So VDD as the input voltage. And this one is VDD. So if both of them are high, then the output is going to be low, 0 volts. Why? This is going to be now linear, off, and off. Okay, so so basically we can consider this to be something like this. For example, for the low output low case, so VDD, and this is going to be let's say A input, and this will be the B input. So the device will be like this, A, B, and Z. Okay, so that's how we make the N and P type or P side. So you can do the implementation of NOR. Basically, this is Z is equal to A and B bar. Okay, so we know that now this is an extra information. This is called the N block. And then this part is called P block. And P block is the complementary of the N block. And we can write the P block as like this, A bar or B bar. So as you see here, A or B, but they are A bar, B bar. Why? In fact, this is why we put these transistors with the bubble representation for the PMOS. And that's how we draw the transistors. So this is going to be how you will be writing N block. But when N block is valid, output will be ground. Okay. So if this is valid, output is going to be high. High if A bar is valid. Or B bar. Or B bar. So with the same concept, we can implement more complicated devices. Here is an interesting device. So this is maybe what we will be calling as the N block. And then this will be maybe the P block. So it should be complementary. So it will be complementary here. So what is the logic? Let's write the logic first. So the logic is, from the equation here, I can write A and B or C and D. When this is valid, output is going to be low. So therefore, there's going to be bar here. So okay, maybe when high, then the output will be low. Okay, so for the P block, we can write the same thing. Z is equal to, let's write the P block first from that drawing. So it is D, we call it bar. Why? Because this is PMOS. Okay, D bar or C bar and A bar or B bar. And that's exactly equal to this one. Okay, so the easiest thing is to draw the N block first, and then draw the P block. Okay, so let's say you want to make a NOR gate, right? And so for the NOR gate, let's say 3 input NOR gate, where Z is equal to A or B or C bar. So how can we implement this? The N block should be like this. A, B, C. The P block should be like this. Now for the PMOS, for VLSI design people, we prefer the transistor to be shown like this. And of course, for convenience, we out. So A, B, and C. Okay, because this thing is going to be equal to A. Did I make a mistake here? NOR gate, right? NOR gate. I made a mistake here. It's not NOR, this is NAND gate. Okay, I need to draw this again. This is NAND gate, right? Either I will erase this or erase the circuits. A little bit larger, maybe. Okay, let me do it one more time. This is going to be A or B or C. A, B, and C. And here it should be complementary. Okay, A, B, and C. We out. Okay, so these are PMOS transistors. Or alternatively, you can draw it like this. And we don't even define the source in these devices. So this is drain and source, whereas this is source and this is drain. Drain, source. Is that okay? You need to tell me if it is okay.
Yes, hocam.
Okay, so just, as a homework, please do this. Or this is the example, not the homework, right? So let's do this one. A and B. Uh-oh. There should be a bar here, right? Because without the bar, it's difficult to implement this. either we put bar here, or we need to put an inverter at the output. So let's put a bar here so that it's more convenient for us to solve. Okay, so A and B, A and B, or C and D, and E is the AND block. So we need to make the P block for this. So E or A, E or something like this. C and D. This one is E and B, VDD. So this one is what? This one is the CMOS one. So this is CMOS. If you want depletion, another alternative is to use depletion load device. Of course, depletion load device is not available in a CMOS technology. Let's do it in CMOS. So therefore, let's forget about this one and then do resistive load. I think we did the resistive load before. Pseudo NMOS. Pseudo NMOS technology. So here you put only one device here, and then the AND block comes in here. And this is P block. Okay, so if we do this and then put here the AND block, this works. So another alternative is to make it like this. You know, we can do many different, versions here. So P block, and then here is going to be VDD, and now we need to keep this always on. So similarly, always on. How can we do that? By connecting here to VDD. So this will also work. Yeah. Okay. So the advantage here is maybe N+1 transistors. And here, N+1 transistors. N is the number of inputs. So here, however, in CMOS, you need 2 times N transistors. But minimum size is okay. Are okay. And swing will be rail to rail, and power dissipation will be 0. Okay, so therefore, people still prefer this complementary CMOS, complementary MOS, or technology. CMOS technology has 2 definitions, both NMOS and PMOS transistors are implemented. Okay, so, but here, even though both transistors are implemented, complementary logic in CMOS technology means this one. I mean this one. 2 times N are used. Okay. So this is not, I mean, in a CMOS, process, we can implement the following also, but that's not going to be complementary. So like we can do this, right? Remember? This is not complementary, right? Or we can do this and block. But this is not going to be complementary logic. So you might want to be careful about the namings here. So here it's showing the slide CMOS inverter versus ideal inverter. The CMOS inverter is almost very close to ideal inverter. So it starts from here to here, it goes like that. And then it's here to here, it goes like this. Okay, so the distance here is VTN plus VTP. And this is VDD divided by 2 in a CMOS inverter. You know, here is when VTN is equal to VTP and CAN is equal to KP. How do we obtain that? WL ratio of P is equal to mu N divided by mu P times WL of N transistor. So then, you know, it's going to be switching is sharp and static power consumption is 0 when output is high or low. Power consumption depends only the static or dynamic power dissipation that happens during charging and discharging of the load capacitance. So P dynamic is equal to CL times frequency of operation times VDD divided square. So you know, high to low, low tie switching is going to be maybe not like what you have seen here. And the CMOS, this is going to be like this, maybe, and then this one is ideal. So that's not very ideal, but it's close to ideal. Okay, so there are some other logic families. You know, in CMOS, dynamic logic in CMOS technology. It is sometimes, you know, it is preferred to select some other logic types, and one of them is the dynamic logic. The dynamic logic is the logic where the output is synchronized with the clock. Okay, so if the input is 0 here, you know, when this is 0, when this is 0, this is off, this one is on, or linear, and therefore when that's the 0 thing, output is going to be sitting at high. And output is going to be sitting high when this is the case. So this is the pull down network, or we call this thing N block. So depending on the logic, output is going to be either, so we don't know about this, either low or high. Okay. Depending on N block. So this way, output is going to be switching. If the internal thing is supposed to be low, so this will be switching to here, or it will be remaining at here. Okay, depending on the AND logic. So that's called the dynamic logic. The output is valid when clock is high. Okay, because when the clock is high, then this will be off. So when this is VDD, this will be off. This will be on. That means linear when this is VDD. Okay. So then this clock or CL voltage will be discharged through N block and through this transistor or not. The clock is high. So the output will be synchronized with the clock. So this has some advantages. Maybe you have seen in your EE312 course, clock skew problems. There are some, other things here that you might have seen. So we need here 2 plus N transistors. Again, here, the output swing is from VDD to ground. So there is no issue in there. So minimum size transistors are okay. Because the output is not constantly pulled up. So the CL can be discharged through the N block and this MN transistor. Okay. So the swing, voltage swing is still, voltage swing is rail to rail. So minimum size transistors are okay here. You don't have to do WR ratio, calculations here. So in this dynamic logic, here is shown only for the inverter case. The pre-charge, the Z output is going to be like that. So clock. So what is this one? I don't know why. These are entered here. So when A is, okay, so I guess it's shown here. This is the case when A is equal to so let me do this. And A is equal to okay, let's do this. This is A. And sometimes A is going to be high, sometimes it's going to be low. So if A remains high, what will happen? And then if A goes to low, what will happen? Okay. So if A is high, then A bar, which is Z, is going to be, decreasing. So this will be our output. Otherwise, if this is 0, so this will remain at high. So Z is A bar. Okay, here we need 3 transistors, 2 plus 1 transistor. But that's what happens here. There's a problem with this circuit. We call this part, by the way, pre-charge. So the CL is pre-charged to VDD. But during the evaluation, that transistor is off. So here, CL can be discharged down to ground. Why? Because there is no pull-up. During the evaluation phase. So minimum size transistors are okay. Okay. So again, ratioless design is necessary. So the problem here is occurs if you connect these circuits next to each other. Let's say, I put one more transistor here, okay? Just to make the case more legitimate. Okay, so let's say they are connected to each other, whatever. So here, output 1 is going to be, during the clock low case, it's going to be remaining at high, right? So this is going to be VDD. And then VA, which is equal to VB, okay, is low. They are both low. Output is going to be remain at high, so no problem. Okay, so correct evaluation. And what about VR2? Again, in the pre-charge mode, this will be VDD. And then it will be decreasing. Okay, everything is fine. During the evaluation, this will go up to high, because it always remains high. Okay, now A and B are high. So this is supposed to but this will be delayed, you know, this will be discharged maybe a little bit late. Why? Because there are two transistors on the discharge path. So slow. Okay. So when the this one VR2 or this transistor see that this is it, this is discharged very quickly. And then wrong evaluation. Before the result of first stage. Therefore, we cannot really cascade. Okay, cascade connection of these circuits is not practical. So we will think about solutions, and next time we will put some elements here for achieving this correct evaluation. Okay, I guess the time is up. So I'm going to stop here. Any questions?
No, hocam.